Hey, what's up, Chem peeps? Who's ready for a free response so exciting you'll barely be able to stay in your seats? A student performs an investigation to experimentally determine the molar mass of butane gas, C4H10. A small amount of the pure gas is released from a pressurized container and collected in a graduated tube over water at room temperature, as shown in the diagram below. Boom! The collection tube containing the gas is allowed to stand for several minutes, and its depth is adjusted until the water levels inside and outside the tube are the same. Assume that 1. The gas is not appreciably soluble in water. 2. The gas collected in the graduated tube and the water are in thermal equilibrium. In other words, the temperature of the gas and the temperature of the water are the same. Alright, take a moment, pause the vid, look at the image of the experimental setup and your data table of vapor pressures of water. The following information was recorded by the student throughout the laboratory exercise. Alright, so we know the barometric pressure, temperature of the water, the volume of the gas collected, and the mass of the gas collected. Part A, calculate the, subpart I, partial pressure of the butane gas collected. Alright, for this one, remember Dalton's law of partial pressures. Boom, where the total, or barometric pressure, is equal to the sum of the partial pressures in that mixture. Let's go back up and take a look at our experimental setup. And also think about the lab that we did in class that looked just like this. Part of the reason why we collect the gas over water is to ensure that the only gas that we're collecting, in this case, is the butane gas, and not the oxygen gas, nitrogen gas, carbon dioxide gas, and all the other gas that make up the atmosphere. But remember that even when we collect gases over water, there's still always going to be one other gas mixed in, and that is water vapor. Okay, so we know the barometric pressure, or the total pressure, is 755 millimeters mercury. And because we're told the water levels inside and outside are the same, that barometric pressure is equal to the sum of the partial pressures of the water vapor and the butane gas. Now, at 25 degrees Celsius, you can use this handy dandy vapor pressure of water table to help you determine the partial pressure of water vapor at that temperature, 23.8 millimeters mercury. Boom. So now it's just a very simple algebra problem. I just have to subtract the partial pressure of the water from the total barometric pressure. 755 minus 23.8. Now be careful, to the correct number of significant figures, the partial pressure of the butane gas is 731 millimeters mercury, going to the least precise place value, which is the ones place in this case. Boom. Partial pressure of the butane gas. Subpart I. We're going to calculate the number of moles of the butane gas collected. Oh, classic Pivner. We now know the pressure of just the butane is 731 millimeters mercury. Now that's important. We want the number of moles of butane gas collected. So we need the pressure of just the butane. A common mistake that is made is students use the total barometric pressure. The volume of gas collected, 90 milliliters or 0.0900 liters. Be sure to convert your volume to liters because our gas constant uses the unit of liters. We're looking for number of moles. Our gas constant for millimeters mercury, 62.4 liters times millimeters mercury per mole Kelvin. Temperature of the water, be careful, when you 25.0 plus 273 to convert to Kelvin. Alright, now think about your algebra skills. I'm trying to get number of moles by itself. Currently, I'm multiplying number of moles by 62.4 and my temperature value, which, let's simplify right now, is 298. In order to isolate this variable, I'm going to divide each side by 62.4 and 298. That'll cancel it out on this side, but whatever I do on one side of the equation, I have to do to the other. Calculator time. 731 times 0.0900. Answer. Divided by 62.4. Answer. Divided by 298. Answer. N equals 3 sig figs 0.00354 moles butane. Boom. Fun thing I like to do, make sure my units cancel out. Millimeters mercury cancel millimeters mercury. Kelvin cancel Kelvin. Liters cancel liters. Only thing that's left is moles. Feeling great. Subpart I. Calculate the experimental molar mass of butane. Recall that molar mass relates the mass in grams per number of moles. All right, let's take a gander at our data table. We are told that we collect 0.21 grams of butane gas. And we know from subpart II that our number of moles of butane gas that we collected was 0.00354. So dividing my mass in grams by my number of moles, 0.21 divided by 0.00354, my molar mass to 2 sig figs, 59 grams per mole. Boom. It's actually some pretty good data, pretty good results there. Part B. If the student fails to use information from the table of vapor pressures of water in the calculation, will the calculated value for the molar mass of butane gas be smaller than, greater than, or equal to the actual value? Explain. The pressure used in A part II will be larger. Therefore, the calculated number of moles of butane will be larger. All right, let's go back up to part A and think about that. Remember, in subpart I, we calculated the partial pressure of the butane by subtracting the partial pressure of the water from the total barometric pressure. And that's where we got this value of 731 millimeters mercury, which we used in subpart II to determine the number of moles. Well, if I failed to use the vapor pressure, this pressure value would be larger. I just used the total 755. In other words, my numerator value is going to be larger. This constant and the temperature is going to be the same, so I'm going to end up with a larger number of moles. Oh, math. All right, now be careful. We're asked to determine if the calculated value for the molar mass of butane will be smaller than, greater than, or equal to. Recall that molar mass equals the mass in grams per mole. The mass in grams, our numerator, will remain the same, but the number of moles will be calculated larger. That's our denominator. Therefore, the calculated molar mass will be smaller. Boom. Again, the mass in grams that we use is going to be the same. That's not going to change. But because we used that larger pressure value in A part sub I, we're going to calculate a larger number of moles. Our denominator is going to be larger. Dividing a larger number into that same number of grams is going to create a calculated molar mass that is smaller than what it should be. Part C. Calculate the number of molecules of water vapor in the graduated tube. All right, we're going to come back to PivNert. In the graduated tube, the partial pressure of the water vapor, all the way back up to part A, is 23.8 millimeters mercury. Both the butane and the water vapor occupy that 90 milliliters. It's not like the water vapor is just going to hang out in one section and the butane's going to hang out in the rest, right? They're gases, so they fill their containers. So the water vapor also occupies 90 milliliters, or 0.0900 liters of space. I'm going to solve for number of moles. My gas constant, 62.4 liters times millimeters mercury per mole Kelvin, times my temperature in Kelvin, 298. Calculator time. 23.8 times 0.0900, answer, divided by 62.4, answer, divided by 298, answer. Number of moles equals 1.15 times 10 to the minus 4 moles of water vapor. Now stop, think about this. Look at the calculation that you just did for part C and go up to part A sub II. We did the PivNert calculation for the butane gas in that graduated tube. It exerted a much larger pressure, same volume, same temperature, same gas constant. So I have a much larger number of moles of butane gas than water vapor in that same graduated tube because it's exerting much less pressure. So there's got to be a lot less water vapor banging around in there. Volume, constant, temperature are all the same. So it makes sense that my number of moles of water vapor is less than my number of moles of butane. But don't forget, it wants molecules, so I've got one more step. Remember the relationship between moles and molecules. Of anything, 1 mole, Avogadro's number. To 3 sig figs, we've got 6.93 times 10 to the 19 molecules water. Boom. The student takes the butane gas that was collected and burns it in pure oxygen according to the equation below. Combustion. Part D. Show a numerical setup using dimensional analysis and calculate the mass in grams of carbon dioxide produced if all of the butane gas the student collected completely combusts. Well, remember, we collected how much butane gas in this problem. we collected 0.00354 moles of C4H10. Boom. We want to know how much carbon dioxide we've made, and the relationship there is 8 to 2. 8 to 2. But it doesn't want just moles, it wants grams. So I'm gonna go one more step, and when determining the mass in grams of 1 mole of carbon dioxide, just head to your periodic table, check out the mass of carbon and the mass of oxygen. Add them together and you get 44.01 grams. Calculator time. 0.00354 times 8, answer, divided by 2, answer, times 44.01, answer. If we completely combust 0.00354 moles of butane gas, we're gonna make 0.623 grams carbon dioxide. Boom, done.